Electric cars are often called zero emission, but the full story is more complex. They reduce tailpipe emissions, yet their production requires significant energy and resources. Manufacturing EVs uses electricity, water, and materials, all of which have environmental impact. Batteries are a key part of EVs, and producing them requires mining metals. Lithium, cobalt, and nickel are commonly used in batteries, sourced from multiple countries. Mining these metals consumes energy and can affect local ecosystems if not managed responsibly. Some mines follow strict environmental and safety regulations to reduce impact effectively. Even renewable-powered factories still produce emissions during battery and vehicle manufacturing stages. Transporting materials and parts adds emissions, depending on distance and shipping methods. The global supply chain spreads EV environmental impact across many regions and processes. EVs produce no tailpipe emissions during driving, which improves urban air quality. Reduced air pollution can benefit human health in cities significantly over time. However, EV production emissions are higher than for conventional cars initially. Life cycle assessments help measure emissions from production, usage, and disposal comprehensively. Using an EV over its lifetime generally results in lower total emissions than gasoline cars. The benefits depend on battery size, energy source, and vehicle efficiency. Charging with renewable electricity maximizes environmental benefits and reduces indirect emissions. Charging with electricity from fossil fuels reduces these benefits, but still lowers tailpipe emissions. Consumer choices, such as driving habits and energy use, influence overall impact. Battery longevity is important. Longer-lasting batteries reduce emissions from production per mile. Recycling can recover valuable metals, reducing the need for new mining activities. Not all batteries are currently recycled efficiently, though technology is improving steadily. Second-life battery applications can extend use before recycling, helping reduce waste. Automakers are exploring ways to improve battery sustainability and reuse globally. Transparency in sourcing helps consumers make informed choices about environmental responsibility. EVs are part of a broader strategy to reduce transportation emissions globally. Public transportation, walking, and cycling complement EV adoption for cleaner mobility solutions. Governments incentivize EV use to support decarbonization and cleaner city air effectively. EV adoption alone cannot solve all transportation-related emissions. Holistic approaches are needed. Educating consumers about production and charging impacts improves overall environmental awareness. Marketing terms like zero emission focus on tailpipe emissions, not total life cycle effects. Understanding full life cycle emissions helps prevent misconceptions about EV environmental impact. Innovations in battery design aim to reduce resource use and energy consumption during production. Smaller batteries can lower emissions, but may reduce vehicle range, requiring careful balance. Efficiency improvements in motors and electronics further reduce overall vehicle energy use. Lightweight materials can improve efficiency, but require energy-intensive production methods. Automakers are experimenting with recycled metals and bioplastics to reduce environmental footprint. Renewable-powered manufacturing plants can decrease emissions from EV production significantly. Consumers can support sustainability by considering production and energy source when purchasing EVs. EV benefits are greatest when paired with renewable energy for charging consistently. Charging habits, such as off-peak and daytime charging, can optimize environmental performance. The global transition to electric vehicles is a step toward reducing climate impact gradually. Ethical sourcing of materials is essential to avoid social and environmental harm. Some mining operations follow strict standards for safety, labor, and ecological protection. EV adoption reduces fossil fuel demand, contributing to lower long-term greenhouse gas emissions. Improved battery recycling systems are being developed to recover metals efficiently. Vehicle design can enhance recyclability and reduce environmental impact at end of life. Policies encouraging renewable energy integration increase the overall sustainability of EV use. EVs contribute to reducing air pollution in urban areas where tailpipe emissions are high. Life cycle emissions vary depending on region, energy source, and vehicle size. EVs can complement broader climate strategies like renewable energy expansion and energy efficiency. Consumers should recognize that clean does not mean entirely impact-free. Responsible EV use includes considering charging source, driving patterns, and battery longevity. EV production and recycling processes are improving over time with technology and policy support. Batteries are central to EV performance and have the largest environmental footprint during production. Lithium is commonly used in EV batteries, sourced from countries like Chile and Australia. Cobalt is another key metal, often mined in the Democratic Republic of Congo responsibly or responsibly. Nickel is used in batteries and requires energy-intensive processing to meet production demands. Mining operations follow regulations to reduce environmental and social impacts where implemented properly. Energy used in battery manufacturing contributes to emissions, which vary by location and method. Factories producing batteries may rely on renewable or non-renewable electricity sources for energy. Transporting raw materials to factories adds to the total emissions of battery production. Battery production involves multiple stages, including mining, refining, assembly, and quality testing globally. Producing high-capacity batteries requires more energy and resources than smaller battery options. Life cycle assessments include emissions from materials, manufacturing, transport, and eventual disposal or recycling. Recycling can recover metals like lithium, cobalt, and nickel for new battery production efficiently. Second life applications repurpose batteries for energy storage before recycling, extending their usefulness. Battery efficiency and longevity are critical to reducing overall emissions per vehicle mile. Advances in battery technology aim to reduce reliance on scarce metals and energy use. Solid-state and sodium-ion batteries may offer lower environmental impact in the future. Using renewable electricity during production significantly reduces life cycle emissions of batteries. Factory efficiency improvements and waste reduction strategies further reduce emissions from production. Automakers are exploring circular economy approaches to minimize raw material demand sustainably. Recycling programs recover valuable materials and reduce the need for additional mining globally. Battery design improvements enhance recyclability and reduce environmental impacts at the end of life. Sourcing metals ethically ensures social and environmental responsibility throughout the supply chain. Transparent supply chains allow consumers to make informed choices about environmental impact. Policies encouraging battery recycling help close the loop on materials and reduce waste. Consumer awareness of battery impacts encourages manufacturers to adopt sustainable production practices. Energy-efficient manufacturing and recycling are key to reducing the overall footprint of EVs. Battery longevity reduces the need for replacements, lowering total production emissions over time. Second-life batteries can store energy for homes or grids, supporting renewable energy integration. Sustainable battery production includes minimizing chemical use and reducing water and energy consumption. Recycled metals can replace newly mined materials, conserving natural resources and reducing emissions. Innovative recycling technologies improve efficiency and reduce environmental hazards from battery waste. Manufacturers aim to source materials responsibly while meeting growing EV demand worldwide. Life cycle emissions analysis highlights the importance of battery production and management in overall impact. Battery production impacts vary depending on materials, factory location, and energy sources used. Collaboration across mining, manufacturing, and recycling ensures reduced environmental impact globally. Ethical certifications verify responsible sourcing of lithium, cobalt, and nickel for batteries. Renewable-powered battery production plants can significantly lower carbon emissions during manufacturing stages. Smaller batteries require fewer materials and less energy, reducing production-related environmental impact. Battery innovations continue to improve energy density while lowering resource and energy requirements. Second life and recycling programs are essential for long-term sustainability in EV production. Consumers benefit when batteries are produced and recycled using environmentally responsible practices. Life cycle thinking helps understand emissions from production, charging, and disposal comprehensively. Transparent reporting of battery emissions empowers consumers and supports sustainable decision-making. Advances in battery technology reduce dependency on high-impact metals over time effectively. Battery recycling reduces waste and mitigates environmental impact from mining and manufacturing processes. Second life applications help integrate renewable energy and improve grid flexibility sustainably. Supply chain improvements ensure materials are sourced and processed responsibly with lower impact. Education about battery production and recycling increases public awareness of EV sustainability. Battery improvements combined with renewable energy offer the best path to lower EV lifecycle emissions. Even fully electric cars rely on electricity, which is not always renewable today. In many countries, coal still dominates the electricity grid, creating indirect pollution. Charging an EV at night might rely on carbon-heavy power plants directly. Renewable energy integration is growing, but it is not yet widespread globally. Consumers often overestimate the environmental benefits of driving electric cars daily. The real emissions depend on the source of electricity used for charging. Charging with solar power drastically reduces emissions compared to fossil fuel-generated electricity. In regions with coal-heavy grids, EVs may produce more emissions than efficient gas cars. Fast charging increases energy demand and may use electricity from non-renewable sources often. Home charging during peak hours can stress the grid, leading to higher emissions. Public chargers are not always powered by renewable energy, reducing overall sustainability significantly. Real-world EV efficiency differs from laboratory tests, often producing more carbon than expected. Cold weather reduces battery efficiency, requiring more frequent charging and increasing emissions indirectly. Long trips with multiple charges can further amplify carbon footprints for EV owners worldwide. The energy mix varies by region, making EV pollution highly location-dependent globally. Grid decarbonization is critical for EVs to achieve true environmental benefits consistently. Policymakers must ensure cleaner electricity sources accompany the growing EV adoption worldwide. Countries like Norway show how renewables combined with EV adoption can reduce emissions effectively. Even so, electricity generation for EVs still involves infrastructure and resource extraction impacts. Hydroelectric and nuclear power reduce emissions, but can create other environmental and social issues. Renewable grids alone cannot solve EV pollution without considering battery production and disposal impacts. The full life cycle of EVs must be considered for accurate environmental assessments completely. Charging habits matter. Partial charging often leads to inefficiencies and wasted energy unnecessarily. Smart charging strategies optimize electricity usage, lowering emissions from non-renewable grid sources. Vehicle-to-grid technology allows EVs to store and supply energy, helping stabilize renewable grids. However, widespread adoption of vehicle-to-grid remains limited due to infrastructure and policy barriers. Public perception often assumes driving electric automatically eliminates carbon emissions entirely. In reality, electricity generation and battery production contribute heavily to EV emissions globally. Life cycle analyses show emissions from coal-powered charging can offset tailpipe advantages completely. Hybrid EVs partially reduce emissions but still rely on gasoline, creating mixed environmental benefits. Battery size also affects charging emissions. Larger batteries require more energy to produce. Automakers balance range and environmental impact, but longer ranges increase production pollution significantly. Renewable charging schedules reduce emissions, but require consumer awareness and technological support consistently. Smart grids can optimize renewable energy use for EV charging, reducing carbon impact effectively. Countries with high renewable energy penetration see EVs outperforming gas cars in total emissions. The carbon footprint of EVs varies widely depending on local energy sources and usage patterns. Charging infrastructure itself has environmental impacts requiring concrete, steel, and electrical components. Building charging stations consumes resources and energy, contributing to hidden life cycle emissions subtly. Consumer demand for fast charging can increase reliance on fossil fuels indirectly over time. Energy storage solutions, like home batteries, help reduce emissions but require additional resources. Charging behavior, like frequent rapid charging, can reduce battery lifespan, increasing environmental impact. Renewable energy adoption is accelerating, but not fast enough to fully decarbonize EVs yet. Seasonal variations affect renewable output, meaning EVs may rely on fossil electricity occasionally. Real-world EV emissions are complex, requiring careful consideration of energy mix and habits. Public awareness campaigns can educate EV owners about reducing emissions through smarter charging behavior. Policymakers and utilities must work together to integrate renewables into EV charging infrastructure efficiently. Battery recycling and second life applications also play a role in reducing overall emissions. Off-peak charging during renewable surpluses maximizes environmental benefits while minimizing grid stress effectively. Even electric car fleets cannot eliminate emissions without parallel renewable energy development nationwide. Smart city planning, including EV charging strategies, helps reduce hidden emissions from urban mobility. Consumers, manufacturing electric cars involves complex processes that contribute heavily to overall carbon emissions. The production of EV motors, electronics, and plastics consumes enormous energy per vehicle. Steel and aluminum production for car frames releases substantial greenhouse gases into the atmosphere. Lightweight materials reduce vehicle weight, but often require energy-intensive production methods nonetheless. Vehicle assembly plants consume electricity, water, and chemicals, producing additional emissions and waste regularly. Global supply chains extend environmental impact far beyond the car factory itself directly. Shipping raw materials and components across continents adds significant carbon to the vehicle life cycle. International freight relies heavily on fossil fuels, creating hidden emissions in every EV produced. Automakers source parts from multiple countries, complicating transparency and sustainability efforts globally. Complex logistics networks make tracking carbon footprints from production nearly impossible for most consumers. Vehicle electronics, including sensors and computers, require rare earth elements often mined unsustainably. Precious metals like neodymium and dysprosium are essential for motors, but environmentally costly. Mining rare earths produces radioactive waste in some regions, posing long-term environmental hazards. Labor conditions in some manufacturing hubs remain concerning, adding social impact to environmental issues. Outsourcing production to low-regulation countries often reduces costs but increases ecological damage indirectly. Assembly lines produce emissions from heating, cooling, and equipment operation, contributing to the carbon footprint. Energy-intensive coating, painting, and finishing processes release volatile organic compounds into the atmosphere. EVs require advanced battery management systems, which add electronics production emissions significantly. Even small components like connectors and wiring involve resource extraction and energy use globally. Automakers are exploring sustainable materials like recycled aluminum and bioplastics to reduce impact. Innovation in manufacturing efficiency can lower emissions but requires substantial investment and technological upgrades. Some companies invest in solar-powered factories to reduce electricity-related emissions during production. Transportation of finished EVs to dealerships contributes additional greenhouse gas emissions indirectly. Supply chain complexity makes it difficult to calculate exact emissions per vehicle accurately. Carbon accounting must include production, transport, battery, and electricity usage for a full assessment. Life cycle emissions show that production often accounts for a higher percentage than tailpipe emissions. Sustainable sourcing policies are emerging, but not yet universally enforced across the automotive industry. Consumer pressure can influence automakers to prioritize cleaner manufacturing methods and materials responsibly. Some EV manufacturers disclose carbon footprints per vehicle, but many still lack transparency entirely. Ethical sourcing certifications help identify responsible suppliers, but are limited in scope and coverage. Supply chain emissions are projected to grow as EV production scales up globally. Reducing emissions requires collaboration across mining, manufacturing, logistics, and energy sectors simultaneously. Innovations in additive manufacturing can reduce waste and energy usage in vehicle production efficiently. Circular economy strategies, like recycling materials within production, can significantly lower environmental impact. Closed-loop battery and materials recycling programs are critical to sustainable EV manufacturing long-term. Automakers experimenting with sustainable factories aim to reduce water and energy consumption dramatically. Digital twin technology helps optimize manufacturing, lowering material waste and energy use effectively. The automotive industry is slowly adopting renewable energy in production, but faces logistical challenges. Global trade of car components means emissions are spread across multiple countries unknowingly. Shipping batteries separately from vehicles adds additional emissions to the supply chain footprint. Regional manufacturing hubs closer to consumers can reduce transport emissions but require local resources. EV production emissions are higher than gas vehicles initially, but usage emissions can offset them. Longer battery life reduces production demand, lowering emissions per vehicle over time significantly. Manufacturers face pressure to balance environmental goals with cost, efficiency, and performance needs. Raw material scarcity increases competition, encouraging more mining and associated environmental degradation globally. Ethical production practices often increase costs, but reduce social and ecological harm sustainably. Supply chain transparency allows consumers to understand environmental impact. Achieving truly clean electric cars requires innovation across batteries, manufacturing, and electricity sources. Solid-state batteries promise higher energy density and lower environmental impact than traditional lithium-ion. Sodium-ion batteries could reduce reliance on scarce metals like lithium and cobalt significantly. Recycling technology must improve to recover most materials safely and efficiently from old batteries. Second life applications of EV batteries can store energy for homes and grids effectively. Circular economy approaches reduce the need for new mining while minimizing environmental damage. Manufacturers are experimenting with bio-based plastics and recycled metals to lower production emissions. Renewable-powered factories can dramatically reduce the carbon footprint of vehicle manufacturing globally. Energy grids must transition to wind, solar, and hydro to support cleaner EV charging. Vehicle-to-grid systems allow EVs to store renewable energy and release it when needed. Consumers can optimize charging habits to reduce emissions, like charging during renewable energy peaks. Government incentives for clean energy charging stations encourage more sustainable EV use nationwide. Transparent supply chains help consumers choose vehicles with ethical and environmentally responsible sourcing. Companies investing in closed-loop battery systems aim to minimize waste and environmental harm. Smaller, lighter batteries can reduce production emissions while maintaining adequate vehicle range efficiently. Public transportation and shared EV fleets can complement private EVs to lower overall emissions. Urban planning promoting cycling, walking, and EV car sharing further reduces pollution effectively. Smart grids coordinate renewable energy, EV charging, and storage to optimize energy use daily. Research into alternative battery chemistries may eliminate the need for cobalt or nickel entirely. Life cycle emissions analyses guide policymakers and consumers in making informed, sustainable vehicle choices. Ethical mining certifications ensure raw materials come from environmentally and socially responsible sources. International standards can enforce sustainable battery production and recycling practices consistently worldwide. Innovations in modular battery design allow easier recycling and replacement, reducing environmental impact. Consumers should consider long-term impacts, not just tailpipe emissions, when choosing EVs responsibly. Sustainable EV adoption requires combined action from governments, manufacturers, and individual users. Research in green hydrogen may complement EVs by providing cleaner energy for heavy transport. Battery leasing programs reduce upfront costs and facilitate recycling and second-life reuse efficiently. Automakers exploring alternative materials like aluminum and magnesium lower production energy requirements. Consumer awareness campaigns help people understand hidden emissions and environmental trade-offs in EVs. Renewable energy adoption must accelerate globally to maximize EV environmental benefits consistently. Life cycle-focused policies encourage manufacturers to reduce emissions from mining, production, and disposal effectively. Innovations in AI and data analytics optimize supply chains, reducing unnecessary resource consumption dramatically. Collaborative international efforts can standardize sustainable practices across the global EV industry efficiently. Clean transportation requires balancing technological innovation, renewable energy, and ethical resource sourcing. Even future EVs will require monitoring, maintenance, and responsible disposal to remain environmentally friendly. Governments and companies must invest in sustainable infrastructure to support growing EV adoption responsibly. Advances in battery longevity reduce replacement frequency, lowering cumulative environmental impact significantly. Electric vehicles are a critical tool, but not a complete solution for climate change alone. Renewable electricity, sustainable materials, and smarter urban mobility together create truly clean transportation systems. Consumers can drive change by choosing sustainably produced EVs and charging with renewable energy. Policymakers must support cleaner energy grids, ethical sourcing, and efficient recycling frameworks globally. Future EVs will be cleaner, but continuous innovation is necessary to approach zero emissions fully. Second life battery programs create value while reducing environmental risks and raw material demand. Companies must integrate circular economy principles to reduce emissions throughout the vehicle lifecycle effectively. Public awareness of hidden EV emissions helps push the industry toward more sustainable practices. Investing in renewable infrastructure and smart grids is essential to maximize EV environmental benefits. New battery chemistries, like solid state, promise safer, lighter, and more sustainable energy storage. Sustainable EV Pro.